Everyone. Today we'll work on number 15.3 in the last section of chapter 7. So there are 3 parts. Part 8, we're going to show the given series converges. Indeed, the structure tells us that this is an alternating series. So we could consider to apply AST. Moreover, we can use some other method. For example, consider the absolute value version. We know this will provide a upper bound for the original one. Okay, by getting rid of the negative sign, and this is just 1 over k squared, and the resulting series is just a standard P series where P equal to 2. We know this is a convergence case. This actually indicates the absolute convergence. Then, of course, it will imply the convergence of the original series. This is part A. Part B, compute S10, then just apply the definition, plug in the numbers. Now we obtain a number like this. Also, we need to figure out an interval containing the actual values, all right? And we already knew the difference between L and S10 will be bounded above by n plus 1, here n equal to 10. So we need to evaluate A11, all right? So we can do this. Now, based on this inequality, we know the true value L is just sits between those 2 particular numbers, all right? Part C, we want to find out the smallest value of n such that we can achieve it. We have the guaranteed accuracy 10 to the negative 6. Now, the similar idea to part B, we know the arrow term is controlled by an plus 1. So if we can solve an plus 1 less than 10 to the negative 6, now we can solve the required n. Okay, so indeed, it turns out that n need to be greater than 993. All right, but that just means the smallest n that we will require will be 1/4. Okay, a very quick recap. In part A, we show the convergence of an alternating series. In general, we could consider to apply AST or apply the ratio test for absolute convergence, or we just simply evaluate the convergence of the absolute value series. All right. Part B, we compute the partial sum approximation and also find out an interval containing the actual values. Part C, with the given accuracy, we can use the bounded estimate to figure out the smallest number of n that we will need to use in the partial sum approximation. Okay, thanks for watching.